Welcome to the live interactive session for the course Surface Water Hydrology being taken by Professor Dr. Rajiv Maiti from the Department of Civil Engineering, IIT Kharagpur. I am the teaching assistant Aman Srivastava, and today in this session we are going to solve some numerical problems on flood routing concepts. So our primary focus will be to solve some problems on Muskingum equation and Nash model. So let us start with the first part, that is the problem on Muskingum equation. Let me read the problem. The Muskingum routing equation is given as Q2 is equal to C0 I2 plus C1 I1 plus C2 Q1. If the value of C1 is 0.42 and the value of C2 is 0.35, then what is the value of C0? So it's a very straightforward question where we need to find out the C0. So let's see how to estimate this. So our first step is to find out the C0, for which the Muskingum equation also provides this equation which is on your screen. C0 plus C1 plus C2 is equal to 1. So now the value of C1 and C2 is already provided. So using that we can actually estimate the C0 value, which comes as 0.23. So it was a very straightforward question. I hope you were able to capture the essence of this equation and how to utilize this to find out the unknown such as C0. Moving ahead, let's solve the another problem on Muskingum equation. For the Muskingum method of channel routing, it is given that the value of the storage constant is 13 hours and the value of the weighting factor is 0.2. Determine the value of C0 if the routing interval is 11 hours. So in my understanding, let us see how we can actually take the approach in solving this question. So first step is to find out C0, the unknown coefficient which is not provided in the problem. So to estimate C0, we can use this equation on your screen, minus kx plus 0.5 delta t divided by k minus kx plus 0.5 delta t. So here k is 13 hours which is provided in the problem, x is 0.25 and delta t is 11 hours which is already shown in the problem, as we can see. Right. So substituting all these values, we get C0 value as 0.1475. So that was the final response to that question. Let us solve question number 3. That is the problem on Nash model. Let me read the problem. In case of the Nash model, the ratio of the second moment of IUH, that is instantaneous unit hydrograph, to its first moment about its origin, t equal to 0, is given as 50 for a particular catchment. Determine the number of identical linear reservoirs representing the entire catchment if the storage time constant is 10 hours. So let's see how we can utilize the given information to find out the identical linear reservoirs required in the given catchment. So first step is to find out the ratio of the first moment and second moment of the instantaneous unit hydrograph about the origin. So how to find out the first moment? Here the equation is shown. This is the equation to be utilized to find out the first moment about the origin. Likewise, this equation can be used to find out the second moment about the origin. And in the step 1, the objective is to find out the ratio of the first moment and second moment. So here the m2 by m1, here we are actually finding putting the numerator as n plus 1 k square and denominator as nk, and solving this we get n plus 1 whole bracket k, see, as the ratio of the first moment and second moment. In the second step, we need to find out the number of identical linear reservoirs, that is n, which is the actual target of the problem. So how to find that? So currently we have m2 by m1, which is 50, which is provided in the problem already, and that ratio is nothing but n plus 1 by n plus 1 whole bracket k, and n is what the identical linear reservoirs that we need to find out. So if we compare this n plus 1 whole bracket k with 50 and substituting the value of k which is already provided in the problem, then which is k, then we can find out the identical linear reservoirs n, which is n is nothing but 50 by k minus 1. It is just rearranged this equation. This equation was rearranged to get the value of n, which came as 4. So 4 is the final response, where we can actually this is the number of identical linear reservoirs which is required in the given catchment. I hope you were able to understand how we can actually use the moment around the origin concept to arrive at the number of identical linear reservoirs. So today in this series we actually solved and understand the nuance behind Muskingum equation and Nash model. Thank you. Stay tuned for more such videos on surface water hydrology. Thank you.